Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content useful, please consider liking, commenting, sharing, and most importantly, subscribing to our channel. Those are all free, very quick, simple things that you can do to help us out, to help us grow. Let's get into the video. Throughout the following discussion, I'm going to assume that you either are familiar with integration by parts, or you've at least watched the integration by parts part 1 video that I posted a few weeks ago. Again, so that means that you should be familiar with the technique. Couple of things. One, recall the integration by parts formula applies to when I have a product in my integrand. Doesn't necessarily guarantee that it'll work, but again, if I have a product, that's one of the necessary conditions for integration by parts to work. And if I have that, u dv, then the integral is uv minus the integral of v du. So again, this is what I'm assuming you are familiar with. In particular, here's just a reminder example. If I've got a product of x and sine of x, remember what I do is I choose my u and my dv, which again has to incorporate this entire expression after the integral symbol. And the way I want to choose this is so that hopefully this integral is simpler. That's the whole goal, is to take a complicated integral and break it down to a simpler integral. All right, so if I make the following choice, u is x and dv is sine of x dx, here I take the derivative, here I take an antiderivative. And again, what I'm going to integrate is v du, so this product hopefully is a simpler integrand than this one. And of course, in this case, it is. What I want to do is, before I do some examples, is let's talk about guidelines for choosing your u and your dv. Because I could have reversed this order right here, and I could have said, so algebraically this would be correct, but I could have said u is sine of x, dv is x dx. Well, differentiating here gives me du is cosine of x dx. And of course, here taking an antiderivative, v would be x squared over 2. So again, there's nothing wrong with that choice algebraically, but then this right here would give me the following result. X squared over 2 sine of x, there's your uv, minus the integral of this product, giving me x squared over 2 times cosine of x dx. So this integral is equal to this. However, notice the resulting integral here is more complicated than what we started with. I went from a x to the first times a trig function to x squared times a trig function. If I integrate this, I will get the right answer. However, it's just more work. So therefore, this was the better choice. So let's talk about guidelines for choosing our u and our dv. All right, first requirement. I need to be able to take the derivative of this. Okay, so I need to be able to differentiate this function right here, which of course I could differentiate both of them. So therefore that doesn't really narrow it down. But again, I need to be able to differentiate my choice of u. I also need to be able to find the antiderivative of the choice of dv. Notice going from here to here, I took an antiderivative. Therefore, that was a solid choice. However, once again, I can take an antiderivative of both of those. So once again, this doesn't narrow it down. But those are two initial requirements. I have to be able to differentiate here and find an antiderivative here. Okay, so now let's narrow this down even further. If I can do antiderivatives and derivatives of both of those functions, if I can find those, well, now let's choose u based on the following hierarchy. So the higher in the list I have, that's going to be my choice of u. First and foremost, if I have a logarithm or an inverse trig function within my integrand, that would be my ideal choice of u, if that appears. Then the rest of it would be your dv. If I don't have that, but I have a polynomial term, for example, x, or maybe an x squared over 2, then that would be my next choice of u. If I don't have those, but I do have an exponential or a trig function, that would be my third choice. Okay, so let's go through a variety of examples of integration by parts where we'll have, a handful of these expressions appearing in our integrand. So let me go ahead and clean up the board. So for the integral of the inverse tangent function, excuse me. All right, so what do I have in my integrand? I've got tan inverse, and then I've got my differential, right? So if I look at this hierarchy, again, tan inverse could either be my u or my dv. Kind of silly to choose tan inverse as dv because this ultimately says what's the antiderivative of tan inverse. So an integration by parts choice, if saying dv is tan inverse, then I have to find the antiderivative of tan inverse. So that in and of itself kind of narrows down your choice. But again, inverse trig function is one of my initial choices in my hierarchy, so therefore we'll choose u to be tan inverse. So therefore dv would be dx. Differentiating tan inverse, we get 1 over 1 plus x squared dx, so that's one of your standard derivatives you should know. Over here, antiderivative of 1 dx would be x. Okay, now using the integration by parts formula, I get, so uv, so I get x tan inverse minus the integral of this product The hope is that this is a simpler integral. So look at that for a couple of seconds and think about how you'd integrate that, and then I will do the next couple steps. Okay. Well, this one is applicable to a u substitution. Different from this u, but so I'll do this in a different color. Let's say u is 1 plus x squared, then du would be 2x dx. Notice I've got an x dx, I don't have a 2, so therefore we can put a factor of 2 in there, and we also would then have to cancel it. Okay, this would then give you so x tan inverse minus a half integral of 1 over u du. And again, we went from a complicated integral to a more workable one and an even more workable one, right? So this one right here, 1 over u, antiderivative should be familiar as the natural log. Indefinite integral, so I need my plus c. And then finally, I need to convert all of this back to the original variable, and I can simply do that by replacing u with 1 plus x squared, giving me the following final answer. Okay. Quick comment, notice I went from absolute value bars to parentheses. I take an antiderivative of 1 over u, since the function 1 over u could have negative values, u could be negative, we have to force it to be positive since it's inside a natural log. The expression 1 plus x squared is greater than or equal to 1 for every x value, therefore the parentheses here, absolute value bars, would be redundant, but they're not incorrect. But here I need those and here I do not. All right, let's take a look at another example. Okay, I have another product within my integrand. This time I've got two distinct functions, whereas over here I had tan inverse. I mean, you could say tan inverse in one, but here I've got two distinct products, two distinct functions of x. All right? And if you remember from that hierarchy, we had both exponentials and trig functions in the third item on the list. So let's just pick something and roll with it and see what happens. Also, of course, e to the x and sine of x, we can differentiate and find antiderivatives of both of those, so that doesn't really narrow it down. So again, that's when I had to go to my hierarchy. All right, so then dv sine x dx, v would therefore be negative cosine of x. So let's see what we got. All right, I get negative e to the x cosine of x minus the integral of negative e to the x cosine of x dx. Two negatives there, so what I'll do is I'll just make that a positive. Well, the resulting integral is not really simpler than what we started with. It's still a product of two functions. One's an exponential, one's a trig function. So let me humor you, and let me just try it again, right? Let's just do another integration by parts on this and see what happens. Okay. So now I'm going to say u. I'll choose u as e to the x again because it worked so well the first time. So then use e to the x, so du would be e to the x dx. dv would then be cosine of x dx. And v would be sine of x. All right, so let's see what we got. Well, first and foremost, I still have this first term plus, now I've got uv minus the integral of v to u well, when we look at that and we say, all right, well, this is what I started with, and it's equal to this line, and then therefore it's equal to this line. What I get is the original integral back. So does that mean that this exercise never ends, and I would just do integration by parts on this, which should give me one of these, and integration by parts again, which can give me another one, so on and so forth? Well, of course, no, because now if I just use algebra and I add this integral to the other side, we're going to get twice the original integral. Is equal to these two terms. And then just divide by 2. So this is a special case of an integration by parts technique where the original integral appears later on down the line, and then we just add that to the other side, and then I can just divide by 2. Okay. This doesn't come up very often, but there's, of course, you can imagine if I started with e to the x cosine of x, that would be another example where this technique would apply. But it would not work if this is a hyperbolic sine or a cosine. Again, why is that? I'll let you think about that. And if you're not sure, post in the comments below. Okay, let's do one more example. Okay, for our last example, let's look at the integral of sine of the natural log. Let's compare it with this one. So this one has a product of two functions of x. This one is a composition of two functions of x. We'll make integration by parts on this work. However, what I have to do first is a change of variables. Said differently, I have to start with a u substitution. Now, remember from the u substitution technique, we have to have a product and a composition, and the choice of u is always the inside of the composition. Okay, so the choice of u inside of the composition, and then we just have to work with that. There's not really any other choice. All right, so therefore, u has to be the natural log. So then du would be 1 over x dx. Okay. Now, this is the inside of the composition, and this is going to have to appear as a factor. Of course, it does not. Well, if it doesn't, here's what I'm going to do. I'm going to write this as sine of the natural log of x, and I have to have that x in there as a denominator for my differential. But if I put it in the denominator, I have to also put it in the numerator. This is constant or frequently used, I guess pun intended by saying constantly, if I have a constant. Because if this was a 2, I could put a 2 here, but then I could just pull the 2 out front. But this is a variable with respect to what I'm integrating, so therefore I cannot pull it outside the integral. Okay. All right. So first and foremost, this expression here is equivalent to this expression here. Now, if I want to do a u substitution with these two choices, or this choice and this result of that choice, that's going to be u. This is going to be your du. This dx is going to get absorbed into the du as well. What about this x here? Because everything inside that integral has to be related to the variable u that I'm substituting. Well, there's a relationship between u and x given by this equation right here. If u is the natural log of x, then this is equivalent to x is equal to e to the u. So let's see what all I'm going to replace. This portion right here is going to be your du. This portion right here, squeaky marker, is going to be u. And this x is going to get replaced with e to the u. So everything there that has an x gets replaced with something that's related to the variable u. Go ahead and plug those in. I would get e to the u, sine of u, du. Well, that integral should look familiar. It's literally our previous example. I just have a different variable. It's a dummy variable, so I can use whatever, whatever letter I like. But the integral of e to the u sine u du is the same as the integral of e to the x sine of x dx. And the answer is right there. So therefore, this would be negative e to the u cosine of u plus e to the u sine of u over 2 plus c. If I didn't have this result handy, like it was in our previous example, we're sitting right next to this work, we know how to integrate this by using the integration by parts technique twice. All right, and then finally, I have to convert this. This is sort of, I call this informally my u antiderivative. I have to convert it back to an x antiderivative, and I simply do that by replacing every u with the natural log of x. I get negative e to the natural log cosine of the natural log plus e to the natural log sine of the natural log all over 2, and then plus c. And then we can just do one little thing to simplify. E and the natural log are inverse functions, so their composition reduces to the input, meaning I can replace, rather than erasing all that and having you watch me erase and then rewrite the answer up on top, I'm just going to say make sure you replace this with x, and make sure you replace this with negative x. And that would be your final answer.